particular order. And so what we should do is we should start with the lowest approximation, which would be to say, well, if they're a long ways apart, you won't see the size of the sphere, so they will simply look as point charges at the centers of the spheres. So your first approximation would be to put a charge Q1 at the center of that, Q2 at the center of that. And that would give the lowest order approximation to this, which should be valid when L over R was vanishingly small. Okay? But now we know that the voltage on the sphere has to be a constant everywhere on the surface of the sphere because it's a conductor. So everywhere on the sphere, the voltage must be a constant. So this will not make the voltage on this thing a constant. We already know that because we know if we put a point charge over here, forget this thing is a sphere, to make this thing a constant voltage, you had to put an image charge in here. And so, to make this one a constant voltage, you would put an image charge, call it Q1 prime, in here, and we know how big it should be. It should be, if this distance right there was L, then we know that Q1 prime was minus Q2 R over L. And we know it was separated, moved from the center, a distance h1, which was R squared divided by L. So, if we make that arrangement with that point charge over there, this thing would have a constant voltage on it. Would what?
Is that Q1 prime or Q2 prime?
I'm calling this Q1 prime.
What is it, the image of Q2?
It's the image of Q2 in this sphere.
Okay.
Okay, but now, if I've got these two charges over here, this will not be a constant voltage. What I will have to do is take the image of this in this sphere and the image of that in that sphere. So that will give me two image charges over here. Making sense? Now, that will make this fine, but this one will no longer work. I will have to put the images of these two in this one. And I proceed in this fashion, but each time the terms are getting smaller. And I take this out to order R over L cubed. Okay, so at that point, what I would have is this at a constant voltage, this at a constant voltage approximately up to that order, but they wouldn't have the right charges on them. They would have that would have made the voltage on them each zero. But when the voltage is zero, the charge is not zero. And so what you then need to do is to add a charge at the middle, which is the sum of all the making the charge at the middle plus all the other things you put in here. In other words, a charge here, you need the sum of all these things adding up to Q1. And so to make that work, you may have to put a charge at the center. So you got two conditions. One, you make the voltage everywhere, voltage on the surface of that sphere a constant. That makes it a conductor. But it doesn't necessarily put a charge Q on that conductor. So now you figure out what the charge Q is on the surface of the conductor. And you do that, you know the electric field, the relation between the electric field and the charge. Remember that on the surface of a conductor, the electric field out was given by 4 pi k sigma. That was the normal component of the electric field. And so since you know the electric field now everywhere on that sphere, you can add up the charge everywhere on it and see whether it comes out to be Q1. And if it doesn't, you put a charge in the center, which is what you need to get the total charge up to Q1. So that's the way you do the first one. And that one is a messy, hard problem. It's harder than the other two put together just because the algebra is messy. The idea isn't bad, but the algebra is messy on that.
So
Yes.
If we're going to the third order, does that mean like back and forth three
Yeah,
times?
well, not necessarily 3 times because it's falling off fairly rapidly. As I recall, I don't remember, I think it had to do 2 times. Let's see. I ended up let's see, how many did I have to do? Okay. Yeah, I needed to carry it to, 3 times. I had to go to 3 times. Right, there you go. See, that's why you're all such great students. You understand how this works. Okay. Now, another way you could have gotten at least the second order would have simply been to say, well, I know what happens is that I'm producing charges at the center and charge next to it. That's making dipoles. And I could have looked at the energy produced, by dipoles. So you could have done it that way. I thought about doing it that way, and I decided that was actually a little messier even than this. But okay, the second problem. The second problem is both of the others are much easier. The second problem, where you got this infinite dielectric plane over here, and you got a point charge out here. So let's just take the coordinate system, use polar coordinates. That's Z and rho. And then you split the thing into 2 regions, 1 and 2. And we suspect we can solve this problem by images. And so we guess that you would want to put, since you have to make it, the boundary conditions apply everywhere on the plane, put an image charge over here, a distance L behind the surface. Okay, now, in region 1, you have to satisfy the equation where you can't change the charges that are in region 1 because they're fixed. But you can do anything you want over here. And so we put an image charge over here of Q prime. Now, when you're looking in region 2, you can't do anything over here. So you can't put a charge over here. But you can do anything you want out here. When it was a conductor, we knew there should be no field over here, so we just made the charge 0 out there. But now, it's a dielectric. There will be a field in here, because this won't be perfectly successful at canceling the field. So we said, okay, let's just reduce the charge so that it comes fairly close to canceling it, but not completely. So we'll put a charge Q double prime there when we are finding the field in region 2. So when we're finding the field in region 1, our system looks like this. When we're finding field in region 2, our system looks like that, with this going. Now, having done that, everybody okay? Having done that, now you can write down the voltage in region 1. It'll be the voltage produced at some arbitrary point up here, R and Z and rho, due to this charge plus this charge. And that's just simple Pythagorean theorem. It would be, for this one, it would be KQ over this distance, and that distance is rho squared plus z minus L squared, square root. So you can write V1, and you can then write V2, and then you get the electric field by taking the gradient of this and the gradient of this one, and then you get the D's as kappa epsilon 0 E. So in this one it's epsilon 0 E, here it's kappa epsilon 0 E. And then since there's no charge on this surface, the boundary conditions are that D normal is continuous, E tangential is continuous. That gives you two equations and two unknowns to find Q double prime and Q prime. And now once you've got that, you've got the electric fields everywhere. You can then find the polarization in here, because the polarization was chi E times E. You know E in here. You know chi E because you know kappa. So you can find the polarization. Then you know that the effective charge density was minus the divergence P. So that's the volume polarization charge. And you know the surface polarization charge was just the normal component of P. So you got that. And then the force between this will simply be this charge times this charge divided by the distance between them squared. So that problem is very straightforward. Well, this is the famous example of hindsight. Now that you know how to do it, it's straightforward. Yeah, I'm trying. I'll persuade you if something is straightforward. Name, let's see. No, I knew it this morning. Okay. Okay, what's bothering you about this?
Like, don't even know where to start. There's just so many symbols and stuff like that. Like, if you knew where to start and, like, one at a time, it's like, oh, okay. But just, like, looking at the problem and getting bogged down and, like, trying to go from one equation to another, to another, to another.
Okay, so the way to go at this, forget all of the arithmetic. Just ask yourself what physically is going on here. And what's physically going on here is I stick a charge out here in front of this big plane. And what's that charge going to do? It's going to produce a field in the space around it and a field in the dielectric. Now, what is going to happen in the dielectric when you put that field there? Well, it's going to cause the atoms to polarize a little bit. It'll cause the positive charges to move one way and the negative charges to move the other. Okay? So that means that I'll get a field that is produced not only by charge Q out here, but also by these dipoles that are being produced in the dielectric over there. When it was a conductor, what happened was you didn't get any dipoles in the dielectric. Instead, you drew charges onto the surface of the thing. And what we did then is we said, well, all those charges on the surface will produce the same effect as though I just put a charge equal and opposite to the original one behind the surface the same distance. And I knew that because the voltage on the conductor had to be 0 or constant, and therefore this one had to cancel that one at all points. The voltage due to this had to cancel the voltage due to that. That meaning they needed to be the same distance away, and they had to be the same magnitude but opposite sign. And so we had decided we'd have minus Q on the left side, a distance L behind it. Now when it becomes a dielectric, we suspect the same symmetry will work, because since I have to make the conditions balance, everywhere along that plane, I have to have these two boundary conditions. I suspect I'll need to put it the same distance behind as it was in front, otherwise I wouldn't be able to make it work at all rows. But there's no reason to think the magnitude should still be the same. In fact, there's every reason to think it won't be, because I know the dielectric is not perfectly successful at canceling the field. So I put in a charge Q prime there, which is not necessarily equal to minus Q. And before, when I was looking in region 2, I knew there was no field. I could do that by just replacing Q with 0. That then would produce no field in the conductor. But now there will be a field in the conductor, just smaller than you might have expected. So I'll just replace Q by Q double prime instead of 0. So now I've got the setup. And now, in order to determine the sizes of those, before I used the requirement that I made the voltage on the surface of that conductor 0, because it was a grounded conductor. So I made the voltage 0. Now, when it's a dielectric, I use the general boundary conditions, that since there's no charge on the surface of that, the normal component of D is continuous and the tangential component of E is continuous. And so that gave me two boundary conditions, therefore two equations, and there were only two unknowns in the problem, Q prime and Q double prime.
So what do you write those as then? Like, I understand that they're continuous, but what equation would you write to solve for Q and E?
Okay. Let's look at V in region 2. Okay, now what is V in region 2? Well, it's due entirely to this charge Q double prime. Because in region 2, that's the only thing I've got. What's what? Yeah, but I'm finding the voltage in region 2. And when I find the voltage over here, I have to be honest over here. There's no charge here. But I can be dishonest out there. Because I have to satisfy, our standard, our equation, del squared V equals minus 4 pi k rho. There is no charge density in here. No real charge density. So I can't have this. When I'm finding the voltage here, the world looks as though there's just one charge in it, Q double prime located there.
Why would it be Q?
Because in here, I expect that the effect of this will be reduced because of the dielectric. And so I don't know what it'll be, but I say, okay, I'll just do that by changing this to Q double prime instead of Q. When it was a conductor, what did I make this? I made it 0. So that I got 0 field over here. Because in the conductor, there couldn't be a field. Now, when I'm out here, I can't change this. So this will have to stay Q, but I can put anything I want over here. Okay, so now, what is the distance from this charge to some point up here, rho and Z? Well, this is at rho equals 0, so the Pythagorean theorem is just this squared plus this squared, and this is this one minus that one, so it's Z minus L. So this becomes rho squared plus Z minus L squared to the 1/2. So everywhere in this region, Z is negative, so it becomes a positive sign, but that's what it will be. Now I can find the electric field. It is minus the gradient of V. Okay, so what is that? That's minus rho hat d by d rho minus c hat d by dz minus theta hat over rho d by d theta applied to this thing, k q double prime over rho squared plus c minus l squared to the 1/2. And so I will get minus rho hat. And I have to take the derivative with respect to rho of this. So I get k q double prime. And now the derivative with respect to rho gives you a minus 1/2 times 2 rho divided by rho squared plus c minus l squared to the 3/2. So that's the rho part. Now the z part. Well, you get k q double prime. You'll get minus 1/2. You'll get twice z minus l. And you'll get this thing, rho squared plus c minus l squared to the 3/2. Now there is no theta dependence here, so that term goes away because there's no theta dependence. So the electric field then, E2, is kq double prime, that factors out of everything, rho squared plus z minus l squared to the 3/2. And now here I have the 2's canceling, the minus signs canceling, and so I get rho hat. And here the same thing happens, and so I get plus z minus l z hat. So that is the electric field in region 2. Now, in region 2, D2 is kappa epsilon 0 times E2. D is always kappa epsilon E. That was our definition.
What is D? What is like the?
That is the displacement, which was D was epsilon 0 E plus P. And that's why we ended up with the equation divergence of D was equal to rho. Okay? Now, that means that the tangential component of E at the plane, which is z equals 0, is the tangential component is the rho component, because that's the one that's parallel to the surface. And so what you get is k q double prime rho, and then z is equal to 0 at the surface. So this is simply rho squared plus L squared to the 3/2. So that is the tangential component of E at the surface. The normal component of D at the surface, the normal component is the Z component, because that's what's perpendicular to the surface. And so it is kappa epsilon 0 times the normal component of E, which is k q double prime. At z equals 0, this is just minus L. And then downstairs, same as before, rho squared plus L squared to the 3/2. So now you've got the tangential component of E, and you got the normal component of D. All right, now you do the same thing for region 1. Only then, the V is the sum of the voltage due to this guy and the voltage due to this guy. And you do exactly the same thing, and then you set E tangential 2 equal to E tangential 1, and D normal 2 equal to D normal 1. This side involves only Q double prime. The other side will involve Q and Q prime, and that'll let you solve for Q double prime and Q prime. And at that point, then you will have the electric fields everywhere, because the electric field is just this. Now for arbitrary Z and rho, so you got electric field everywhere. Now to find the polarization in the dielectric, you remember that since it's a linear dielectric, it was chi sub E times E. And you know the electric field, it's this thing, so you can find the polarization. And we knew that from that D, which was kappa epsilon 0 E, was equal to epsilon 0 E plus P, and therefore P is equal to, from this, kappa minus 1 epsilon 0 E, but that's chi sub E times E, so you can find what chi sub E is, and therefore you can find what P is. And then we knew that the effective charge density due to polarization was minus the divergence of P, so you can find that. And we knew that the surface charge was simply the normal component of P at the surface, so you can find that. And to find the force on this charge, as far as this guy is concerned, the only thing there is in the universe is this Q prime over here. So the force will be Q prime, be K, Q prime, divided by this distance, which is 2L squared. All the symbols and things make sense now?
They make more sense.
This is progress.
So I get how to find electric field in 2 and 1.
Uh-huh.
Sorry, how does that relate to finding it everywhere?
Because 2, the way I've written it there, that's any value of Z and rho you put in, that gives you the electric field. That's everywhere.
Then why do we need to find the electric field in the first as well?
Because we want the field everywhere. That means region 1 as well as region 2. To find the polarization, you only need it in region 2, because that's where you got a dielectric. But to find the field everywhere is both region 1 and region 2. And you couldn't have found the Q and Q prime, the Q prime and Q double prime, without knowing E in both of them, so you could match the boundary conditions at the surface.
What did you do after you did the effective charge density? What's the last equation?
Remember, what we had done is we looked at when you had varying polarizations in here. The fact that you had a different polarization here than you had here meant you had a net charge, because this arrow, this is a positive charge, this is a negative charge. There's a bigger positive than negative. That gave you charge density, and it turned out to be that. At the surface, all you had, there was no one over here. All you had was this, and so this charge was just that, and that's the normal component of P. And so you had an effective charge density on the surface, which was just the normal component of P, where normal meant the component perpendicular to the surface.
So how would you solve that?
Okay. You've got this. So what is the normal component of P? It's this times the normal component of E, and the normal component of E is this guy, the Z part, with Z equal to 0. So the normal component of P will be chi sub B K Q double prime times minus L divided by rho squared plus L squared to the 3/2. If you work through this problem carefully and be sure you're understanding each of the steps, you will thoroughly understand dielectrics. This does everything. That's why I put it there. Everything connected with the dielectric is in this problem. And so it's worth your time to understand what each of the steps mean, what each of the entities mean. Feeling better?
Better.
Doesn't look totally hopeless now? No, this is progress. Now the third problem is just a simpler version of the one I did in class. It's simpler because the battery is disconnected. That means that there's no energy associated with the battery because it's out of the picture. And so all you have to do is take the gravitational energy plus the electromagnetic energy. Where before we had that plus the battery. So this is just a simpler version of the one we did in class. And the dielectric gets sucked into the capacitor because the energy, electromagnetic energy, will go down as you put a dielectric between the plates when you can't change the charge. When you had the battery there, you could change the charge. But when you can't change the charge, then as soon as you put a dielectric in there, the electric field goes down by kappa. And because the electric field goes down, since the energy per volume was epsilon 0 E squared, that stuff. Since the electric field went down, the energy went down, and so the system will move up because it'll always go to the lower energy. If the electric field were really straight across everywhere, of course you couldn't get an upward force because the force is parallel to the field. But at the edges, you get fringing. And that's why you can get an upward force. But how would you ever solve it that way? You have to know exactly what the fringing was. So it's easier to do it in terms of energy because then you don't care about the fringing as long as the height is large compared to the fringing distance, which is a pretty good approximation. More terror is setting in.
So in the polarization, how would you find the chi sub E again?
Well, we go back to our definitions. We defined, originally D is this. That's what it is. Now, if it was a linear dielectric, what we said was that P was proportional to E. And so this became epsilon 0. This became, right here, D, which is kappa epsilon 0 E, was equal to epsilon 0 E plus P, which is chi sub E times E. And so looking at this, you could cancel out the E's. And that meant chi sub E was kappa minus 1 times epsilon 0. Is there a what?
Should the epsilon not be canceled out by another epsilon naught in the denominator on the D?
You've got D is kappa epsilon 0 E, but it's also this, epsilon 0 E plus P, which is chi sub B times E. So if I divide out the E's, I get chi sub B. I just bring this one over to here, so I get kappa minus 1 times epsilon 0.
K equals 4 pi naught on the left, and then on the right it's so I think it's there's a K on the left and then a chi on the right.
You agree with this?
Yeah.
Well, I should say you agree with this right here. If I divide out the E's, I'm left with kappa epsilon 0 equals epsilon 0 plus chi sub B.
Yeah.
And so to get chi sub B, I subtract epsilon 0 from each side.
Let me just on the 3, 4 equations up. The one next one up. So there, I think they're E naught in the denominator for the E field, and the E field is capital L.
Well, there's a K here, and the K is 1 over 4 pi epsilon 0. Right. Okay. So now let's go on with where we were yesterday. Somebody wrote down for me what we gotten to.
Can you explain one more time what the third problem was? It was without the battery additional that we did in class. So it would be the gravitational potential.
And the electromagnetic, but no battery because I've disconnected the battery before I lowered the thing into the dielectric.
Okay.
So no charge can be taken to or from the battery, so its energy can't change.
Okay.
Okay, so we were working out, great.
Could you explain, sorry, one more time, the process for doing the image charges for the first one?
Yeah, you start, the lowest approximation is put each charge at the center of the sphere. And that's what it would look like if you were very far away. You couldn't see the size of the sphere, so it just looked like at the center. But now, that arrangement will not make a constant voltage on the first sphere. So you image that one, the Q2 that was on the center of the right-hand sphere in the first-hand sphere, and that gives you an image charge Q1 prime here. Okay? But now, that pair of charges will not make the voltage, constant on this one. So you image each of those in this guy. And now this one is happy, but now this one is not happy. So now you got to image the two you just added over here in this one.
Doesn't that go on forever?
That's right. It goes on forever. It's an infinite series, and that's why I said get the answer to the third order in R over L.
Okay. So you want like Q1 prime, which would be the image of Q2, and then you want the two of those imaged
Over
on
here, and
the
you
line.
do that until the terms you're getting for the forces are
Smaller, they don't.
smaller than R over L cubed. Okay, so last time we were working out the magnetic field that would be produced by a little current loop. I'm sure this is obvious, but clearly this is a different kind of class than others you take, because I'm not concerned with ranking everybody and this sort of stuff. I want you to learn. And the exams are supposed to be learning experiences. So I don't mind giving you a lot of help in doing an exam, because you're all great students. We don't have to worry about that. But I want you to have the opportunity to learn. And the best way there is for that is to be doing something where you care what you get. You have to be concerned that you do things right, but then you get enough guidance that you can actually do it. Okay, so what we had was that the magnetic field at position x, y, z was K magnetic times I divided by r cubed times the integral. Theta goes from 0 to 2 pi of x hat z cosine theta plus y hat z sine theta plus c hat r minus y sine theta minus x cos theta d theta divided by 1 plus r over r squared minus 2xr over r squared cos theta minus 2yr over r squared sine theta to the 3/2. So that's where we had gotten to last time. I'm sorry, what? Yeah, there should be an R written outside here, I guess. Just he didn't have it in the notes here, but you're right. There certainly has to be. Yeah. Okay. So that's exact. But now we're interested in the situation where this is going to be a little tiny current loop. Now what does little tiny mean? It means that the big R should be very small compared to little r. Because little r is how far you are away from this thing. And if you want a infinitesimal loop, then no matter how far away you are, the little r is very big compared to the big R. That's what you mean by making the loop infinitesimal. So I'm going to expand the denominator according to the binomial theorem, which was 1 plus x to the n is 1 plus nx plus n minus 1 over 2 factorial x squared, and so on. So all of these things are small because they're of the order of r over r quantity squared. So I write this as B is equal K sub m I r over r cubed integral 0 to 2 pi of that thing in brackets times 1 minus 3/2 r over r squared plus 3xr over r squared cos theta plus 3yr over r squared sine theta times d theta. Okay, now that's K sub m I r over r cubed. Now the x hat term will involve z cosine theta integrated against this. And so I will have a z, and now I will have the integral of cosine theta times 1 minus 3/2 r over r squared plus 3xr over r squared cos theta plus 3yr over r squared sine theta d theta. That's the x part. Now, what happens here? What's the integral of cosine theta from 0 to 2 pi? Well, obviously it's 0. Obviously it's 0. Right? Because the integral is sine theta, and that between 0 and 2 pi is 0. That's a constant times that. So that integral is 0. Now this one is the integral of cosine squared. And the integral of cosine squared from 0 to 2 pi, the average value is a half. You integrate from 0 to 2 pi, and so you get pi. And this one is 0 because the integral of sine cosine is 0. So this whole thing then is k sub m I r cubed times pi times z times 3x r over r squared. So that's the x part. Okay? Now we've got to do the y part. Now for the y part, exactly the same thing is going to happen because the integral of sine, see I'm taking the y part there, which is z sine theta, and I'm integrating over here. That'll be 0, that'll be 0, this will be 0, but that will give you pi. And so all that happens is I'll get plus z 3yr over r squared y hat. And then finally I got to do z. Well, for z, what I've got is this thing. So now I'll write this out, 0 to 2 pi. And now I have r minus y sine theta minus x cosine theta times this thing, 1 minus 3/2 r over r squared plus 3xr over r squared cos theta plus 3yr over r squared sine theta integrated d theta. Okay, so what are we going to get here? First we do this one. And when I integrate r on this stuff from 0 to theta, I will just get 2 pi r. When I integrate it on this, I'll get, well, so I can put these together, so let's do that. So I have 2 pi times r minus 3/2 r squared over r squared. That's this times this times this. But the integral of cosine and the integral of sine are both 0, so those go away. So then I've got this one, minus y. Now, integral of sine is 0, so that's 0, that's 0, that's 0. But here I got sine squared, same thing as before, so I get pi. So I get minus y times 3yr over r squared pi. And then I got to do this one. Well, exactly the same things is going to happen, except I'll get minus x times 3 minus x times 3xr over r squared pi. And so it's this thing times z hat. So that is what the magnetic field should be. Now we'll combine these things. We'll combine these things together. There should be a pi. Thank you. Thank you. Okay. Now, we put these things together. Stop the stupid thing. Can't even shut it off. It's ridiculous. Okay. So let's see what we got here. Let's factor out a pi and an r. And if I do that, then I get I times pi r squared, which is the area of the loop. And so I get B is equal to K sub m over r cubed times I times the area of the loop. Okay. Now, left inside, I have 3 x over r squared times z. Now, let's suppose that I were to guess that this thing is going to look like a magnetic dipole whose value is I times A and whose direction is perpendicular to the loop, therefore in the z direction. So if we take this to be the dipole, then what happens is that this term, see what we found before was this. It was K sub m times K sub m over r cubed times 3 m dot r times r over r squared minus m. That's what the magnetic field due to a dipole would have been.
Where did the A come from?
Pi r squared.
Oh, so you factored out
I factored out an r, and that gave me pi r squared. And that's the area of the loop. Okay, so what would the x component have been? Well, the dipole is in the z direction, and so this thing would have been the magnitude m times z, and then this would have been, I'm looking for the x component. The x component would have been x, and it would have been divided by r squared. And there's no component of x for m because it's entirely in the z direction. So I should have had inside mzx over r squared. I factored the, when I wrote it, where did I write it? I factored the, I thought I wrote it down here. I factored the pi r outside, and that made the I times A. And then the x component is z times 3x over r squared. And so that would be 3 times zx over r squared. So the x component matches. In exactly the same way, the y component matches. And so all we have to do is worry about the z component. And everybody following okay? So now I need the z component of this thing. And for that, I go to this, and I write so here's z. So I factored a pi outside of this thing, and I factored an r outside of this thing. So I had pi r, and then left I had 2 times 1 minus 3 halves r over r squared minus 3 y over r squared minus 3 x y squared over r squared, 3x squared over r squared. Okay, now what I'm going to do is I'm going to subtract a minus 3 z squared over r squared, and then I've got to add a 3 z squared over r squared. I took those over there. But I've got a mistake here. There's the dimension wrong here. So where did I screw up a dimension here? Because this thing is r, and that's dimensionless. So the z part there, first I integrated the r, get 2 pi, r minus, this should have been an r cubed. And so when I factored an r out, this was an r squared over r squared. Okay. Now, this term right here is x squared plus y squared plus z squared, which is r squared. So this thing is minus 3. And so what I've got is minus 3 plus 2 plus 3 z squared over r squared minus 3 r squared over r squared okay. And now this term completes this one. Remember, I had this thing for x, y, and now this piece completes the z squared part. And what I'm left with then, that one, so this one is out. And here I'm left with minus 1 times the pi r, and I've already factored out an IR, so that's m. And so the bottom line is this. So what happens is that a little infinitesimal current loop produces exactly the same magnetic field you would have gotten from a magnetic dipole. I times A in the direction given by the right-hand rule. is my grandson. And he calls 17 times a day. And